There are two major types of AC machines, which are synchronous machines and induction machines, induction or asynchronous machines. So synchronous machines would require an external DC power for the magnetic field current, but induction machines do not require an external source. Magnetic field current would be induced through a transformer action. Therefore, no external DC source would be required. The field circuit location is on the rotor on most basically AC machines. We will be covering the fundamental concepts common to both synchronous and induction machines in this chapter. So let's first talk about the MMF and flux distribution. In reality, AC machines have a ferromagnetic rotor with a small air gap between the rotor and the stator. So here, the inner circle shows a cross-section of the rotor, and the outer basically figure is showing the stator, and these basically are the windings on the stator. So we have two schemes in here. This scheme, figure 412A, is called the round rotor. As you can see, the rotor is pretty much in a rounded shape, but figure 412B is showing a salient pole rotor, which means that the rotor is not completely rounded. It has some salient poles that are mounted on the rotor at these locations. Therefore, this causes the air gap between the stator and the rotor to be non-uniform. So as you can see, here we have more air gap, here we have less air gap. But in the round rotor motor, we have a pretty much uniform air gap between the stator and the rotor. Okay, so cylindrical rotor or round rotor, this is the same as round rotor, or non-salient pole, these are all the same. They provide uniform air gap, whereas salient pole, which is this scheme, has non-uniform air gap, as can be seen in these schematic figures. The flux path and sinusoidal voltage generation. The air gap obviously has a higher reluctance where we have air gap compared to the rotor and the stator, because rotor and stator both have basically ferromagnetic materials. Therefore, the reluctance inside both the rotor and the stator would be very small. But when basically the magnetic field reaches the air gap, it sees a much bigger reluctance. Therefore, in order for these magnetic lines to pass between the rotor and the stator, they choose the minimum resistance or reluctance path, which means that these magnetic field directions would be perpendicular, would have a perpendicular path across the air gap. So they would go on a 90 degrees out of the rotor and into the stator, or out of the stator here and into the rotor, if that makes sense. Armature is on the stator, and your field would be on the rotor. So let's see what happens in here. To generate sinusoidal voltage output, in the case of a generator, these sinusoidal output voltage would be induced on the stator winding, which is on the armature. So to do that, flux density must also vary sinusoidally along the air gap. So this is only possible if the magnetizing intensity and magnetomotive force would vary sinusoidally. Keep that in mind that these armature windings are on the stator, so they would be fixed. There is no rotation in the armature windings on the stator. Basically, a time-varying sinusoidal field can be created by the armature windings, and at the same time, you can basically put some DC current and on the rotor windings and rotate it and cause a time-varying sinusoidal magnetic field to be felt by the stator armature windings, if that makes sense. So let's see how this is possible, starting from stator or the armature windings. So this is showing a very simple structure associated with three phases. So AA prime, BB prime, and CC prime in this manner. So in each of these three sets of conductors, we are basically having a sinusoidal current flowing. So that happens on the stator. So the current in phase A would be I max cosine of 2 pi FST. The current in phase B and phase C would have 120 degrees of phase shift with respect to phase A. And because of these currents, you would be having MMF, which passes through the area, and that MMF would cause a flux density also. So these are the flux densities. We all know that flux density is a vector variable, which means that with respect to the space, it has some direction. And also, because these currents are time varying, your flux density would also be time varying. So it's not only a space vector in the sense that it has a specific direction. So, for example, for the flux density of phase A, this would be the direction of that vector because it's at angle 0. So this is angle 0. And for phase B, it would be at angle plus 120 degrees with respect to this BA. And for the flux density in phase C, it would be minus 120 degrees with respect to phase A. So these three vectors that you're seeing on this figure are basically associated with those space vectors, the vectors that do exist in this space. But the vector has basically a magnitude value. It is time varying at the same time. And it is time varying with these basically equations. So cosine B max, the maximum would be B max, but there is a sinusoidal portion that would be multiplied by that. Cosine of omega st, cosine of omega st minus 120 for phase B, and cosine of omega s plus 120 for phase C. So the net basically flux density of this setup would be when we add these three vectors together, right? B net associated with the stator would be when you add up these three vectors together. So when you do so and watch basically how your flux density is varying over time from the perspective of an external viewer, so somebody who is watching basically this setup from outside, you want to see, or he wants to see, how this basically flux density is changing over time, or the magnetomotive force is changing over time. It would be as if you would have a permanent magnet like this, and you would be rotating that with a rotational speed of omega s inside this stator. So if that makes sense. So the result would be the same. And basically, you have a synchronous speed. So omega s is the rotational speed in radians per second. If you want to express that in RPM, that would be called n synchronous, which would be equal to 120 times Fs over P, where P is the number of poles in the machine. So in this setup, as you can see, we have only 2 poles. So it would be as if a 2-pole magnetic permanent magnet would be rotating inside this setup. Okay, so we can have a 4-pole setup like what we did for the 2-pole setup. A 4-pole setup would be as if you have a magnet carved like this, a permanent magnet, where you have 2 n poles, 2 s poles, and you're rotating that with the synchronous speed, what we call the synchronous speed. So how that works using this setup, its equivalent would be as if we would have 2 basically phase A's, so A1, A1 prime, A2, A2 prime, 2 phase B's, 2 phase B conductors in these locations. So B1 prime, B1, and B2 prime, B2, and 2 phase C conductors. So that would be C1 prime, C1, and C2 prime, C2. So if you have this setup, now it works as if you have a permanent magnet like this rotating at a specific speed, which we call it the synchronous speed, or the rotational speed of your rotating magnetic field. So this brings us to some definitions. So the first definition is pole pitch. So pole pitch would be the angular displacement between the North Pole and its adjacent South Pole, which should be always equal to 180 electrical degrees. So let's look at this setup, which is a 2-pole setup. Traveling from north to south would be 180 degrees electrical and 180 degrees mechanical, right? Now, in the 4-pole setup, when we want to travel from north to south to its adjacent South Pole, you see that we go for only 90 degrees mechanical. but that 90 degrees mechanical would be the same as 180 degrees electrical displacement. So this brings us to the definitions of angular displacements in the sense of electrical versus mechanical. So electrical displacement in radians, or theta E, would be P over 2 times theta M, where theta M is the mechanical displacement in radians, and P is the number of poles in the machine. So as you can see, if the machine is a 2-pole machine, theta E would be the same as theta M. But if the machine is 4 poles, has 4 poles, theta E would be 2 times the theta M. So that's why basically 180 electrical degrees in a 4-pole machine would translate into 90 mechanical degrees. Since displacement, or in other words, since speed, rotational speed, is the time derivative of the angular displacement, so we can conclude that in terms of rotational speed, the same type of relationship also would exist between the mechanical versus electrical speeds. Now we're talking radians per second. So omega E would be P over 2 omega M, where E is the electrical speed, whereas omega M is the mechanical speed. Now, I talked about this very simple setup, which I said would work like this permanent magnet, which is rotating at a certain speed, which we call it the synchronous speed. Now, it is true that the maximum of the field would be happening at these poles, right outside of the North Pole and outside of the South Pole, right? So this is maximum, and at this point would be minimum. But when you take a snapshot of this, what we really want is that we would be maximum at this point, and then we would be varying basically the magnetic field in a sinusoidal way, so that we go from maximum to minimum, and then from maximum to 0, and then from 0 to minimum, and then from minimum to maximum, from minimum again to 0, and then to maximum, like a sinusoid, right? So this is what we expect. We want to go from, here is the maximum, right? Then every 90 degrees we go from maximum to 0, and then from 0 to minimum, and then to 0, and then we come back here to maximum, and we repeat ourselves. This is our expectation in a sinusoidal waveform, right? So we expect that this setup gives us something like this. At this point, I would have the maximum, and then when I reach here, I would get to 0, and then to minimum, and then here again to 0, and then here to maximum. In a sinusoidal manner, the changes should be sinusoidal, right? So this setup, the reality is that this setup does not give us that exact sinusoidal behavior as we wish, okay? So what I'm trying to say is that this shows you the concept. Yes, the maximums and minimums would be happening at these 2 points in a snapshot, but in order to see the time variation of this magnetic field to be like a sinusoid, you really need to have a more complex setup. So when we're talking about, for example, the conductors, how the conductors should be put, they really need to be put in this way. So this is showing the setup for a single phase, okay? But what we really need to do is that for the same phase A, you should have the maximum number of conductors at these 2 points, at these 2 areas. So these are all slots with some conductors in each of these slots. So you would be like having 10 conductors here, 10 conductors here, 10 and 10 in here. And then you have to have like 7 conductors here, and then 3 conductors here, 3 conductors here, 7 conductors. So this is showing basically a distribution of the number of conductors around the surface in this stator in order to gain a specific magnetomotive force, which even at that time would be not sinusoidal completely, would be something like a stepwise, like a sinusoid. Although the concept in AC machines is simple, but the realization of those concepts would be very complex in real manufacturing of the machines. So we talked about the concept of, yes, I want each phase to basically distribute an MMF, which is like a sinusoid. right? But that is not as simple as that. You really have to have a specific setup to try to make that pattern in a sinusoidal way, if that makes sense. So this is just something to note. So this was only for phase A, and now for phases B and C, you can imagine that you would need to have some phase shift with respect to some extra slots in here that would be belonging to the other two phases in the same specific manner with some phase shift, if that makes sense. All right, so in that case, like here, it's 0 in here, then goes to a maximum, and then goes to 0, goes to a minimum, and comes back to 0 when you are basically traveling around that stator. So to gain that, this would be the theoretical number. So NC would be NE times cosine of alpha, where alpha is this angle. So at alpha equal to 0, it means that you should not, you should put the maximum number of your conductors. And as alpha grows, so for example, when alpha becomes 90 degrees at this point, you would have the minimum. So number of conductors would be 0. So don't get them wrong with the maximum of the field. So here you have the maximum number of conductors, but through the right-hand rule, that would cause this point to have the maximum field. So look at here, this simple setup in here, A prime. So use your thumb in the direction out of the page at this point, and for other figures, other fingers would point the direction of the field to be this way, and this would be the maximum point, the maximum. All right, if the current is basically at this point, you would get the maximum field at this point. So that's why the number of conductors would be maximum where the field is minimum, and would be minimum where the field is maximum. So in summary, it is not easy to get a sinusoidal distribution of the flux. You have to come up with a lot of basically tricks and schemes and manufacturing designs. So some practical challenges. So so this stepwise pattern would add a lot of harmonics. In order to reduce those harmonics, you would have to come up with a lot of ideas in practice. The number of slots, we know it's finite, right? So in reality, it's preventing a perfect sinusoidal distribution. Conductors per slot are whole numbers, so you cannot have fractional number of conductors. This would cause deviations from ideal sinusoidal form, which leads to harmonic. And some concepts are here. Fractional pitch windings are used to reduce unwanted harmonics. What does fractional pitch mean? Simply, it means that a full pitch would be when A from A prime is 180 degrees apart. But if you make A with respect to A prime to be, for example, 170 degrees apart, that means fractional pitch, not a full pitch. So that would result in reducing harmonics. And as I said, it's not easy. It's a complex procedure. Now let's assume that you have a magnet or you have a rotor setup. You have a rotating magnetic field that is existing because of your rotor rotating with a certain speed. And you have a loop of conductor on the stator. Here we had our stator or armature windings creating that rotating magnetic field. Now, I want to say that if there is a rotating magnetic field existing, it will induce voltage on these stator windings. So that's the other way around. So we have a rotating magnetic field that is basically seeing the stator windings. So this is showing one loop of the stator winding that is fixed in space, but because it sees a rotating magnetic field passing through it, we would have a voltage induced on that conductor loop. Okay, so here is that rotating or changing time varying magnetic field that my conductor bars are watching or are seeing. So if the rotating magnetic field is spinning at a speed of omega m, let's assume that your machine is a two-pole machine for simplicity, okay? So omega m would be the same as omega, which is the electric omega in here. This basically, the electrical rotational speed would be the same as the mechanical. So therefore, we would see a magnetic flux density that is expressed as this. So it would be a sinusoidal. Now, to determine how much voltage would be induced, on the conductor loop, we would use the same fundamental equation of E induced would be V cross produced by B, and then inner produced by L, where V is the velocity of the wire relative to the magnetic field, B would be magnetic flux density vector, and L would be length of conductor in the magnetic field. Okay, so this is the basically way that voltage would be induced in the armature windings of a synchronous machine. So in a synchronous machine, you have a rotor that you put windings on the rotor, and you're spinning the rotor, and you are putting some DC currents in the rotor. But because of the construction of this whole setup, when you're spinning that rotor, these basically windings on the stator would see a sinusoidal time varying magnetic field or flux density intersecting them, and therefore there would be some voltage induced on them. Okay, so we want to see how much. So if this is going to be the flux density, then you would see that in the different segments AB, BC, CD, and DA, we would have different types of voltages. So for segments BC and DA, we saw that in the case of DC machines also, that in these two sections, there would be no voltage induced, but in the other two sections, voltages would be induced and they would be just added up together. So we get, in summary, we get the same concept that you had in the case of DC machines. In the case of DC machines, do you remember that the induced voltage was a function of phi and omega? So here, that's the same thing, is a function of phi, the maximum flux per pole, and omega, the rotational speed. But since this is an AC machine, there would be a time variation on the induced voltage, and that time variation would be a sinusoidal time variation. So that cosine of omega t would show you that component. And in general, if you have NC number of conductors, instead of just one single conductor loop, this would be the induced voltage that you would see on those NC number of conductors that are basically existing in that specific slot. So in summary, we have a rotor, there are some windings on the rotor, and there is a current existing in those rotor windings. And while the rotor is spinning, there would be basically a distribution of magnetic field that is seen like a sinusoidal variation, if that makes sense. All right, so if the rotating magnetic field has p poles, then we would have basically the relationship between the mechanical and electrical degrees would be through p over 2, where omega is the electrical speed, omega m is the mechanical speed, or the speed of the rotating magnetic field. Something I want you to pay attention to is that the speed that you're watching, if you are an external, basically somebody who is sitting outside and watching the rotation of the magnetic field, that rotation that you're watching is a mechanical rotation, which is omega m, all right? But then depending on how many poles your machine has, then the electrical speed would be p over 2 times of that rotational speed that you're watching with your eyes. So what you see with your eyes is a mechanical rotation speed. But if your machine is a two-pole machine, that would be the same as the rotation of the electrical angular speed, if that makes sense. But if you have a 4-pole machine, then what you see, if you're seeing, for example, 10 RPM, then really in terms of your electrical degrees, you would see a 2 times of that. So based on this relationship. Now, you can, we talked about just one coil, and then we assumed that coil had NC number of turns, and this would be the induced voltage. Now, assume the fact that you would be having not only one slot in here, which is filled with these conductors, but also 2 other slots with 120 degrees phase shifts with respect to this one slot, okay? Then since as this magnetic field is rotating, it sees this conductor bar first, and then the one that is 120 degrees behind that sees that one, and then the other one. So because of that displacement in space, you can expect that the voltage that would be induced, and we saw it was induced based on that, in the other 2 spots, it would be induced with 120 degrees of phase shift. So that causes your three-phase machine, really. So this would be assumed for the first phase, or phase A. 120 degrees of phase shift would happen for phase B, and 240 or plus 120 degrees for phase C, if that makes sense. In these equations, so here it's showing that distribution. So AA prime, this was the one that we discussed, and we got this for, right? And then this BB prime, CC prime basically shows the other two, which would be 120 degrees phase shifted. Also, I'm seeing here a cosine, and here you see a sine. I would not really get confused with that. I want you to basically look at the concept here. So cosine and sine are the same waveforms, except for a 90 degrees of phase shift, right? So it really depends on where you got your reference. Where was your reference point? Then sine and cosine would be practically the same, except for a 90 degrees of phase shift, which is caused, this difference is caused by changing the reference, really. So I wouldn't get confused because of that. In these equations, NC is the number of conductors in each phase, phi is the maximum flux per pole, and omega is the electrical speed. So I would put a maximum here, maximum flux per pole. Okay, now let's talk about, these are time domain sinusoidal waveforms. If you look at them in terms of the RMS voltage that would be induced, really the Emax from these equations would be NC phi omega. Therefore, also keeping in mind that this omega is 2 pi f, where f is the frequency, then this equation would be 2 pi NC phi f, and then dividing in this Emax over square root of 2 to make the RMS value. You can see that the RMS value of voltage that you would expect in each phase would be based on square root of 2 pi NC phi f. Now, if you are connecting the machine in Y or delta, the line voltage would be different. If the machine is Y connected, then the voltage that you would get would be square root of 3 times of EA. If the machine is delta connected, then the terminal voltage would just be equal to EA. Now let's look at this example 4.2 in the book. We're giving some information about the simple two-pole generator that we just saw. The peak of flux density of the rotor magnetic field is 0.2 Tesla, and the mechanical rotational speed of the shaft is 3,600 RPM. The stator diameter of the machine is 0.5. Its coil length is 0.3, and there are 15 turns per coil. So let's see what these are. This 0.2 Tesla, this 0.5 M, that's the diameter, which is 2 times of the R. The coil length, that's the L, and this is NC. We want to see that machine is Y connected. We want to see what are the three-phase voltages of the generator as a function of time. So as a function of time, the flux in the machine would be given by 2 times RLB, where B is the maximum flux density. So RL, if this is L, and this is 2R, 2R times L, that becomes the area, this area where the flux passes through, right? So consider that. Phi will be found. And then we have phi would be based on that, would be 0.03 Weber. The speed of rotation would be 3,600 RPM. We multiply that by 2 pi and divide that by 60 to get the 377 radians per second. We want to see the magnitude of the peak voltage. That's NC phi omega, 15 times 0.03 times 377. That becomes 169.7. That's the maximum voltage in each phase. And the three-phase voltages would be, this is the maximum times sine of omega t. This is maximum times sine of omega t minus 120 and plus 120 or minus 240, right? The RMS voltage would be just the maximum value divided by 2, square root of 2, which becomes 120 volts. And the terminal voltage, the line-to-line voltage in the terminal would be a square root of 3 times of EA, which would be 208 volts. All right, now we talked about voltage. Now, the same way that voltage would be induced in the machine, like in this case, in the stator windings, we could also have a torque to be induced on the rotor windings due to the interaction between the stator and rotor magnetic fields. So let's assume that the same setup that we had. We have a rotating magnetic field, and we have basically some conductors that are located on the rotor, and there could be some current flowing in them. Okay, so first, talk about the magnetic field. This is how the magnetic field is basically changing with respect to that alpha angle. So here is alpha is equal to 0, and then here becomes maximum, then here becomes 0, minimum, and then 0 back. So based on this equation 451. Also, let's assume that you have conductors in the rotor that are carrying a current of I. This current will produce its own magnetic field, right? So we have two fields here. Let's say that this BS is coming because of the stator. So you have stator windings. You put currents in them, sinusoidal currents, and you created a rotating magnetic field. Is that clear? So that's the same thing in BS is caused by the same thing that we started today with. We put basically sinusoidal currents in the stator. They created a rotating magnetic field. So that is causing this BS. And now, let's say that you have on your rotor, you have some currents flowing in the conductors in the rotor. So this is showing one loop of basically conductors in the rotor where the current is coming out and then going in. The current that will flow inside the rotor will cause its own magnetic field, which we call it the rotor's magnetic field. So here we have two magnetic fields. One is the B of stator, the other is the B of rotor. Now let's see what forces, and then from there, what torque would be induced on that conductor bar that can rotate freely, right? We know that stator cannot move, stator windings, because they're fixed, but we're talking about that rotor bar that can freely rotate or spin. So we want to see what force causes that to happen. This is like putting two magnets close to each other, right? There would be some force between these two happening. So that's the same thing. Here are two fields. One is from the stator, the other is from the rotor. So they would have some force induced upon each other, and depending on which one of those windings is fixed, which one of those windings can rotate, there could be potentially a torque happening. So let's see how this happens. We have two conductors, let's say, conductor 1, conductor 2. So this is the same conductor, which is going and returning, right? But I mean, since this is on the right-hand side of the figure, the other is on the left-hand side. So that's why we can basically look at them separately. So the induced force on conductor 1, based on this famous equation, F is equal to I times L times B, L cross B, which would be really ILBS sine of alpha. And the torque would be R times F, where R is the radius in here, which becomes RILBS sine of alpha counterclockwise. So this would be basically the force that causes a counterclockwise torque. Same thing on conductor B. So on the conductor B, we would get the same basically force in the other direction, which causes the same counterclockwise torque. So when you add them together, tau would be 2 times RILB BS sine of alpha, which would be counterclockwise. So here, R is the radius of the swept circle. I is the current in the conductors. L is the length of each conductor. BS is the maximum of the stator's flux density. Alpha is the angle of the conductor's plane with respect to the reference axis. And we can further look at the torque equation to be, so if that current is existing inside the conductor bars here on the rotor, that causes a magnetomotive force, right? That magnetomotive force can be explained as HR, which is R is rotor. That magnetomotive force is caused by the rotor, which would be dependent on the I, the current, and that C is just a constant that shows that proportionality. Also, the angle between the peak of the stator flux density and peak of the rotor's magnetizing intensity, HR, if you call that angle to be gamma, that gamma would be 180 minus the alpha. So this is geometry, okay? Therefore, there's the sign of alpha would be the same as sign of gamma. So we can write up, because of that, the tau induced as HR times BS times sine of alpha times K, where K is a constant, 2RL over C. And that would be something like this. Tau induced would be K HR cross-produced by BS. HR and BS are both vectors. K is a constant. Tau is your induced torque. So torque can also be treated as a vector. So this is the vector of the torque, tau induced. That's why I put that arrow bar on it. We know that HR cross-produced by BS causes a vector. This constant is a scalar. So this is a vector, basically, production, as you can see. Now, this is HR, which is the magnetizing intensity of the rotor, and this is BS flux density of the stator. In order to represent this equation in terms of the flux density of the rotor, we know that there is a relationship between the flux density of the rotor and H of the rotor through its mu. So therefore, you can represent basically tau induced based on BR and BS, where this small k becomes the big K in here divided by mu. So although K is a constant, but this K capital is a constant, but this small k would not be constant because it depends on mu. And you know that mu could be a variable thing inside the magnetic materials, right? Okay, so the bottom line is that the vector of the induced torque in the machine would be a function of the cross product of the flux density of the rotor by the flux density of the stator. Also, I mentioned about tau to be a vector variable. Now, can you tell me, based on when we're talking about torque would be either clockwise or counterclockwise? How would you determine that a torque is clockwise or a counterclockwise with respect to this cross product? That's through the right-hand rule. So if your thumb is out of the page, the other four fingers show the direction of the rotational speed. All right, so since here F induced 1 and F induced 2 will cause a counterclockwise rotation, it means that your thumb must be coming out of the page. And this coming out of the page is in the same direction as the induced tau. Okay? So if you go ahead and use the right-hand rule, put your HR in the direction of your index finger and your BS in the direction of BS, middle finger in the direction of BS, then your thumb will be out of page. That's another way. Or you can treat it this way. The rotation of your four fingers, non-thumb fingers, wherever they would make the smallest, basically, angle between BR and BS, your thumb would determine the direction of the torque, right? So when you put your thumb out of the page, your other four fingers would show a direction which goes from BR to BS in the smallest possible angle. So that's how you can also determine that your tau induced is causing a counterclockwise rotation. So we wrote the relationship between tau, BR, and BS. We can also write that up in terms of B net, where B net is a net flux density caused by BR plus BS. So tau induced we know was small k times BR cross BS. So from here, you can put the equivalent of BS to be B net minus BR. And then you can just expand this. So this would make this equation. Tau induced would be K BR crossed by B net. So both equations would be correct. Same K in here, same BR in here. Here is BS, here is B net. Keep that in mind. So when you're using this equation, the angle between BR and BS would be gamma. But when you're using this equation, the angle between BR and B net, BR and B net would be called delta. So here is another expression. So I would say that this is these two are the vectors, BR and B net, but these are the magnitudes of the vectors. So I would remove that. So this is just the magnitude of the tau induced, and this is the vector of tau induced, if that makes sense. Okay, so let's talk a bit about the AC machine power flows and losses. So the efficiency of the machine would be the output power over the input power times 100, where output power would be the input power minus the P losses. And basically losses in the machine are in the form of copper losses, core losses, mechanical losses, and stray losses. Where the stator copper losses can be expressed in terms of fleet RA/IA squared, where this 3 is coming from the fact that you have a three-phase machine. IA is the RMS of the current, the magnitude of the RMS current. And in the field circuit, that would be RF/IF squared. That's the rotor's copper losses. In the rotor, we typically have a direct current. So this is not an RMS. IF is a direct current. The converted power is defined as the tau induced times omega m, where omega m is the rotational speed of the rotor, the mechanical speed of the rotor. And tau induced is the induced torque, or sometimes we also call it electromagnetic torque. When we're talking about the flow of power, here we have the input power, tau applied times omega m. So this is going to be a motor. On the input side, you have your mechanical power. On the output side, you have your electric power. So you would be reducing the stray losses, mechanical losses, core losses. At this point, you get the converted power. So converted power would be tau induced times omega m. The difference between P in and P converted would be in the taus. Here you have the applied torque or the mechanical torque versus induced torque or the electromagnetic torque. When you reduce basically the copper losses, you would get the output power in the machine. When you're having a motor, you're giving the machine the electric power. You have copper losses. At this point, you get to the converted power. And then you subtract the core losses, mechanical losses, stray losses to get the output power, which is the tau load times omega m. Tau load is the mechanical torque on the output side of the motor. And when we're talking about generation operation, voltage regulation would be an important definition, V no load minus V full load over V full load. And when we're talking about motor operation, speed regulation would be important, and no load minus N full load over N full load. Yeah, so this was a summary of basically an introduction to AC machines.